Once again, I thank the organizers for letting me come to this meeting. Of course, I am the speaker right after lunch, so there are, well, I can either put you to sleep and you can enjoy and have a good digestion, or I could say something very controversial, and maybe that will also help the digestion, but I will try to stay away from the controversy, and perhaps you can take a little nap. Okay. All right, so what I will speak about is granular mechanics, and we have now created a model to describe some type of granular materials which have damage and plasticity using the principles of thermomechanics. Right. Okay, so my talk will have a brief introduction, then a brief introduction about the granular micromechanics model and how we can derive the model with thermomechanics, and then we'll apply this to certain specific materials and some problem which I think is germane or of interest to everyone in this room. Right. Okay, so the motivation or the introduction, there are many materials, and we heard earlier about bone being very complicated materials. Well, there are many natural materials which are also extremely complex and have granular texture. Right. So when we say granular texture, what we mean is that they can be described as conglomeration of grains of various sizes, and these can range from atomic sizes, and I can give you many examples of these things. Often they are described or characterized by ill-defined structures. So they are granular in nature because you can feel they are granular if you see them by eye. So optical wave propagation is granular. You see them by sound, it's granular. So in many ways they are granular, but they are not easy to define. The granularity or their microstructure is not easy to define. So this is the type of materials that I'm dealing with usually in a civil engineering department. Right. So and we also know that these structures, the granular structure, affects the behavior of these materials. As an example of these material systems, soils and powders are obvious, but in general, all geomaterials such as rocks, Portland cement concrete, asphalt concrete, geopolymers, certain glassy polymers, or even monolithic materials with grain powder precursors, mineralized tissues, as we saw, can be categorized as these type of materials. Right. Okay, so the challenge and what we want to address is to develop some practical material models that are based upon some principles that we can all identify with to describe their mechanical behavior, typically at scales that are amenable to continuum approaches. So we don't want to do discrete approaches. We want to make a continuum model, and then they can provide some insight to the unique behavior that these materials show. I mean, for example, they have inherent and even more importantly loading-induced anisotropy. So as you load these materials, their anisotropy changes, evolves. And usually we have difficulty in describing these things in some conventional way. So this presentation will focus upon rate dependence and tension compression asymmetry of these materials. The target I have is the behavior of what we call hot mix asphalt. So you are all familiar with this. I don't think there's anyone in this room who has not experienced the effect of these things. These are classical materials. Whenever you drive down a road, you have asphalt, and you have experienced some bump, whether you're driving the car or sitting in the car. Okay, so the problem is classical. But there is a lot of room for improvement, as you know, right? As I'm sure when you walk on the road, you see all these materials have unraveled, or they have formed what we call ruts, which are depressions in the pavement caused by driving over it over years. They are affected by at the local scales between grains by water, by the environment. So there are many things that we need to still learn about these materials, and it affects billions and billions of dollars worldwide. Right? So it is not a new sort of material, for example, metamaterial, but it is important to our general economy and wellness, right? So this is the scope of the project, of this presentation. So just to give you an example of the type of behavior that we need to describe, this is some experimental result of creep test and creep recovery tests on these type of materials at 20 degrees Celsius, that's a nice temperature, at two different loading levels, and of course they are clearly nonlinear, and they have irreversible deformations, and they also have damage happening during this type of loading. So the existing way of dealing with these problems in tensorial analysis is the usual viscoplasticity, and there you have to require a specification of plastic potentials, damage functions, and even more importantly, the rules of their evolution, which can be very complicated. They have to be motivated by experiments, and the experiments are not easy to do for these kind of materials. Okay, so the approach we will take, and which I've been working with for many years, is this granular micromechanics, and I've been searching for a name for this type of approach. So finally I've settled on this name. The idea is that we view these materials as made up of grains. So grains may be easily defined or not, okay, but at the grain level we can define some local intergranular constitutive laws, and then through some processes we can upscale those to a macro or a meso level, right? Okay. I just want to note that the microstructure is not well defined, so these microstructure, the granular structure, is somewhat notional. In some cases you can of course identify the grains, so in the case of clean sands, for example, you can find exactly what a grain is, and you can maybe try to describe the intergranular relationship through theoretical techniques, but here it's not always necessary that we have easily identified grains. So the grains can be notional. So where is this approach coming from? So there's a little very brief discussion of the historical context. In the 50s there was a lot of work done by Mindlin and co-workers, and some in the materials area to construct continuum models of packings of grains. So this is for mechanics of sands, right? Okay, but I think this idea has even earlier origin, and I think if we go back to the earliest work of, or very early work of Navier, where he is deriving the equation of balance for deformable bodies, he has a similar notion of some molecules which are not defined, right? So these are coarse grain. So this is another word that is used in this type of approach. It's coarse grained structure, and then he is making some Taylor's expansion to find the balance equation, and as a result he finds a elasticity constant. Of course, this elasticity constant has been thoroughly examined, criticized, and there are in the Book of Love or other historical reviews, people have discussed this thing. But the idea is quite useful, and it is quite powerful, and this is what we will exploit. All right, so much about granular mechanics. So in the past, we've used mechanistic arguments to derive models using that type of approach, the granular approach. But in this presentation, I want to see if thermomechanics can help us explain or understand a little more deeply what may be happening. So the first equation I'm sure you're all familiar with. This is the Clausius-Duhem inequality. The first term is, of course, the power density of internal forces, and we just take the power density related to the first gradient of displacements. Higher gradient terms, I think there is some work by Pierre-Chepichet which shows that these things can include higher gradient terms. Right? Okay, so this equation is standard, right? And for the type of materials we are discussing, which are rate dependent and have damage and plasticity, we will introduce a Helmholtz free energy of which would be a function of all these kinematic variables, where the one with the superscript V refers to the rate part or viscous part, D is damage, and then the plastic internal variables. Right. So in this work, later we will drop the heat-related terms, so this theta, the temperature will become irrelevant for at least for discussion today. Okay, so that's the expression for free energy. The dissipation is typically in this kind of approach, and this is all standard, this model using a dissipation potential, which is also considered as a function of the rate of internal variables, right? And we can write the dissipation in this form. Right? All right, and it's typical to combine then the free energy expression and the dissipation with the inequality we have to get this formula, which then gives us what are known as the Ziegler's orthogonality conditions and gives us an expression for the Cauchy stress. Right? Okay, so up to here everything is a standard. Okay, so for the granular system, what we see that the free energy will be contributed through the free energy of the intergranular interactions. Okay? So where the intergranular interactions are now functions of intergranular kinematic variables, so the relative displacement between two grains and then the damage related to the two grains, the viscous part, the plastic part. Right. And similarly, we define the dissipation function as the volume density of intergranular dissipation. Okay, so if we introduce these definitions of free energy and the dissipation into our macro scale Clausius-Duhem inequality, we can start to draw some conclusions about granular system. And the first thing that we find is the expression for stress in terms of intergranular forces. Right? Okay, so we see that the Cauchy stress is some volume average of intergranular forces, and this partial derivative term. So I will say more about this later. Okay. All right. The other orthogonality conditions, or what are known as Ziegler's orthogonality conditions, if we introduce those summations in terms of free energy and the dissipation, lead us to, under some conditions, to this local orthogonality conditions, right? So what we're doing here is making saying if n is arbitrary, then we can make term by term equality, and those lead us to these set of orthogonality conditions, which implies that there is a similar inequality as at the macro scale at the intergranular level, right? So we have now obtained a Clausius-Duhem type inequality for the alpha-th intergranular interaction. Okay? And this will then help us determine the constitutive equations for between two grains. Okay? All right, so the rest of the talk will be now more particular to the material that we've talked about. That's the asphalt material. Okay? So in this case, I have assumed a particular expression for the free energy function. First of all, the intergranular interaction we, for convenience, decompose into a term that's along the centroid between two particles and another which is orthogonal to the centroid, right? So N represents this centroidal value, W orthogonal to it. Okay, so we assume now a particular form of free energy function. So first part is of course elastic, there is damage part, there is plasticity part, and I will show you that this thing actually has a physical meaning. So we have, I mean this is not arbitrary, but this is somewhat simpler, so the simplest form that I could think of, right? So that's the free energy, and then a dissipation potential of this form, and I think these things are all well known. They're in books. So if you have viscous term, they are proportional to the square of the rate of viscous displacement. Damage is usually given in this fashion, right? Okay, so if we take these free energy functions and the dissipation potential, use the inequality we saw in the previous view graph, we can find the expression for the force between two grains, right? The expression for this damage modulus, right? Because this has a unit of modulus or stiffness, and expression for the plastic stiffness. Okay, right. So of course there's some algebra that's missing, but that's relatively simple, right? So if we combine those formulas, we can find now the local or intergranular constitutive relation, and it takes this form. Okay, right? So the force between two particles in the normal direction has a stiffness term, some sort of viscous term that's proportional to the rate of displacements, and then there is an additional term which is proportional to the rate of change of force. Okay, so this is like a relaxation term. Now it turns out that this particular form is equivalent to a rheological model of this type, right? Okay. So, in other words, we could have started with a rheological model of this type and obtained a local constitutive law of this form without having to go through thermomechanics. But thermomechanics is giving us an additional confidence about the consistency of these relationships. Okay, so we have the local constitutive laws, and all these are terms derived from previous view graph. The damage function in this case we assume to be an exponential type, so this is the damage function, and also we assume the viscosities to have a exponential decrement with the loading. Now this is not necessary, but the experimental results are best modeled with this additional assumption. Okay. All right. So so far for the loading, of course, we would be incomplete without the loading and unloading part. So we can, in the same way as we do in standard plasticity, introduce a yield function and define all these loading unloading criteria. And in this case, we take the yield function to be just the plastic dissipation energy that we described previously. Okay. So if we use this, which you saw earlier, right, as the yield criteria, then we will find that the dissipative forces are same as what we derived 2 slides ago. Okay. All right. So we have a lot of confidence in this model. So we have the local constitutive law. We can use now the stress, macro scale stress, or the Cauchy stress expression we derived a few slides ago, and complete the constitutive relationship at the macro scale. Right? Okay, so here I want to make a comment, and the comment is that the stress is given not only in terms of intergranular forces, but this partial derivative of the local displacement to the overall strain. right? Okay. And if we define the local displacements to be proportional to some local strain, which is valid only at the grain scale, then we find that we have to think about this term. So in other words, at every grain level, the strains are fluctuating, and they have some relationship to the overall strain of a collection of these kind of grains. Okay, so in general, this relationship, I think we have seen this before, is not easy to define, especially if you do not know the microstructure. Right? Okay. So you can dream up microstructures. Of course, if you come up with some microstructure, you can make a simulation or maybe even find in closed form such relationships. But in general, this is not so easy to define. All right. Okay. But if you assume a mean field assumption that the local strains are same as the macro scale, then you arrive at this relationship of Cauchy stress in terms of the local forces and the vector that joins two particles. Now this equation I want to comment about a little bit, because this is very widely used in granular mechanics. It is also very widely used in molecular dynamics. So when people are calculating stresses in molecular dynamics, for example, they will use this kind of relationship, plus of course they will have the kinetic term. Okay. So what we observe from the analysis we've done here, that this relationship is only valid under certain kinematical assumption, right? Okay. Now, if you want to see the etiology or the lineage of this equation, I think it's traced back to the virial that was introduced by Clausius, and people have used that virial to derive such relationships for atomic systems and for molecular systems. Okay. But it turns out that there is some assumption there. So this is one thing to keep in mind. But nevertheless, I mean, in my talk, I will use this as a starting point and make some practical calculations which are useful for describing the problem of these asphalt. Okay, so we have the summation in terms of interparticle forces and the vectors that join the particles together. If we look at them carefully, they are all functions of direction cosines, and in this case we can try to find an average sigma ij by introducing a probability density function of how many grains you have in a certain direction. One can also introduce a probability density function for forces, and you can find phase averages of these quantities. We can find fluctuations and so on and so forth. So we can deal with only the averages. If we want, we can also work or obtain fluctuation terms. Okay. All right. So this is finally what the constitutive relationship looks like. Of course, these terms are all functions of local forces and local displacement, so we cannot integrate them in closed forms. They have to be calculated numerically. All right, so now very quickly I will go through some practical results. So this model has certain parameters, right? So we have some elasticity parameters, some plasticity parameters, some damage parameters, and these can be obtained by calibrating against experiments. So in this case, we have some experiment on a sample of hot mix asphalt, which is subjected to a creep test, and we can do a optimization process to fit the creep under compression, creep under tension, and then a creep recovery test. So for 3 tests, we can find all these parameters, which all have physical meaning. So then we can try to predict the response of what happens when you're driving on the road. And there are such some simple experiments people have done where they've looked at load time, unload time, etc., and There are many details in these experiments, so we can spend a lot of time. I think one point of these kind of presentation is to show that the model is actually working, which you can see. But if you have interest in discussing details, what are things that we can learn from these things, we can do that later. But so. Remember in the beginning I said one of the aim of this work is to look at the asymmetry between the compression and the tension response. So I have a compression response here, this is the tension response, right? They look very similar but at different values of stress. So that's 1.5 megapascal, this is 5 times the smaller stress, right? Okay. All right, so we can predict creep time to failure, this kind of chimney plot. The advantage of this type of model is that you can follow or you can see how the energies are evolving during this say creep process. So elastic energy versus viscous versus damage energy or dissipations. Okay? And we can also follow how the material is getting damaged in different directions. So this is what's indicating that the material will be experiencing induced anisotropy, right? Loading induced anisotropy. And we can predict these type of failure envelopes or yield surfaces, which in classical viscoplasticity would have to be assumed a priori. Okay. All right, so I think how much I am done with time, right? A few minutes. Okay, so we will go through this. We can implement this type of model in finite elements. The only reason I show this thing is there's a non-standard implementation. So you cannot just take this model and put into Abacus or Adena. There is an additional term that shows up that has to be treated a little bit differently. So it's a non-trivial implementation into Abacus, or you can write your own finite element program. But you end up with the finite element program. And I think I pressed a wrong button, so I need to go up. Okay. All right. And we can simulate what happens to the pavement as you drive over it. Okay. So in this case, we have done 1,000 cycles. So one cycle takes 1 second, so 1,000 seconds, and in 1,000 seconds, so this type of loading, right? Okay. And these numbers are quite realistic. You have 50 millimeters of asphalt that's lying over some base layer, and this tire pressure is what Michelin tire of certain type applies, and that's exactly what we're doing. Okay. All right, so I think the first view graph is not so important. I think this last one, the second one, is more important. So at 2 different loading levels, so this may represent a small car, like maybe I'm driving, or a large Mercedes that Samuel may be driving, would be this one, right? Okay, all right. So so after 1,000 seconds is about 4 hours. Okay, you can generate a 2 millimeter of permanent deformation in the pavement. Right. So now 2 millimeters is not sufficient to make you experience some discomfort. But when we do this over millions of cycles, you can have rutting, and this is what's causing the rutting. But what is even more interesting is that you see there is a little bulge next to the depression that has been caused, and this is what we observe a lot, and you will see some cracks developing there. So some of these effects can be modeled by classical approaches. But so what's important here is you end up with a relatively simple model. You do not have to assume yield functions and plastic potentials and damage functions and their evolution, right? So I think this is the final rutting depth. So if you drive for 1,000 seconds, 4 hours, and then leave the pavement, it will have some recovery depending upon what kind of car. So eventually you have some small displacement, and that will build up into a big rut. So Okay, so maybe I can summarize. So I've combined granular micromechanics and thermomechanics to develop a continuum material model for these rate-dependent materials which have damage and plasticity. I think the main finding from using thermomechanics was that you have the Cauchy stress tensor in terms of microscale or grain interaction forces, but in addition there is some kinematical quantities that come into this expression, right? Okay. So the usual expression that's used in granular mechanics and in even molecular dynamics may have some inbuilt assumptions which sort of become clear, right? Also, we can find a Clausius-Duhem type inequality that's applicable to two-grain interaction. And we can use these type of, we can combine these relationship to find this microscale constitutive laws, which in this case we made applicable to asphalt concrete under repeated and multi-axial loading, and we can predict some practical issues. Right? So I think this is my last slide.
Yes. Given the fact that you have interaction model of comparables with the shear force present, are you not worried about missing?
Louder perhaps, a bit louder if you ask.
Yes.
Louder, because I'm not sure the unit.
Let's go together. Yeah, so given the fact that you have the interaction model with shear force, are you not worried about introducing or neglecting the rotation?
Yes, Right. I'm worried about that type of thing. Yes, of course. And one can include those in this framework, and will bring out other degrees of freedom, and we can deal with that. We are not okay. So this is the first first level model, right? Okay, so yes, one can,
Okay, I know it's very difficult to write a model for granular materials, which on the other hand is correct, on the other hand takes something typical for granular materials. But I wonder if these theories, rate-dependent theories, do they satisfy material objectivity? Or maybe we should say that they are true only for some processes or whatever. This is one question. Another question also, when we have a coupling between, for isotropic materials, between shear and pressure, then we, to write it correctly, we need to consider media, in my opinion. So, and also, should we ask, how would we formulate material objectivity for fabric using fabric tensors? It probably depends on when you take for N, maybe it's a normal in the point of contact, or maybe it's another kind of normal. So what would you say about material objectivity and all the theories presented?
So the framework is in standard continuum mechanics, so it satisfies all the issues of material objectivity. So we are not introducing fabric tensors a priori into this formulation, right? It appears as a consequence of the expression for stress. Okay. And yes, because we start from a microstructural consideration. So I don't think this is an issue. And the coupling between the volume strain and the shear strain, the deviatoric strain, right, also is not assumed. It appears because different intergranular directions are experiencing different conditions at the same macro scale level. So yes, so these theories have many things that are happening at the intergranular level, and yes, of course, one must spend a lot of time to study why such a theory can it's a somewhat simple theory, can predict responses which are quite complex.
Maybe I'm mistaken, but you presented some failure surfaces. Are some theoretical results about convexity properties of this?
Okay, so what I presented is calculations, right? So I calculate by going in different loading directions, and these are all numerical surfaces, so we have not looked into the convexity. Yes, okay, yes, I must say, so the way these things are computed is just in a discrete fashion. Okay, then I have all these discrete points, right? So to show in the view graph, I make some interpolations. Okay, so yes, so also these failure surfaces, how we determine them is an issue. So we're doing numerical calculations, so we have to see whether, what's our failure criteria, right? So whether the acoustic tensor becomes singular.